3 weeks without it, at least 2 weeks without it. Um, you'll have to remind me sometime if I do take a break and turn it off, to be sure to turn it back on, or at the first of class to get it started, or even better, at the end of class, tell me to end it. Last Thursday, first day we had it back, I got my first two classes recorded really nicely. I remembered everything. Then my third class, um, I only had a half hour for my lunch between my third class and fourth class, and and the third class went over a little bit. They had questions, various things. So I was in a rush. I forgot to stop the screencast-o-matic. And then when I came back in, started teaching my fourth class, um, I don't know if I even noticed it, but it was running, so I thought I had started it and stuff. The end of that class, I found out I had 5 hours on there. My third class and fourth class were recorded together. First of third class, then the fourth class. So I've saved them both to both classes and just told the first class, only listen to the first hour and 15 minutes. The last class, skip the first hour and 15 minutes, actually close to hour and 45 minutes, and pick up there and go on from there. So supposedly you should be able to edit the things, but I've never been able to do a clean job of doing that without losing stuff. So I just left them both together. So anyway, remind me, be sure you stop the recording at the end of class. That would be helpful. Thanks. Any questions, issues, concerns before we get going on today's class? Okay. What I'll do is start my screen share from the book. And this means I have to move this taskbar out of the way so it won't be interfering with reading the book. And I think at the same time I'm going to move Ryan, because he's always in the way, up to the top here. You can't see what I'm doing, but y'all show up as blocks on the side of the page or the top of the page. To read the book, it's better for you to be on the top. So I said Ryan, but all of you are listed there. All right, no questions from what we've covered so far? Okay, if you see or sense that anyone else is trying to get in, let me know. I had one student, I know this morning, Jemanuel, his signal was so bad in the dorms, he was not able to get in easily and then kept getting dropped out. But I had a student last week who claimed he sat, and he showed me the screen. He showed me the screen. He said, I sat watching this screen saying, wait for your host to put you in, for about, he said 15-30 minutes or 15-20 minutes, something like that. And I swear I was looking all the time, and I had other students come in late, but I don't know, Zoom just put them in the wrong place or something, I don't know. And I never saw them out there. And so I told him to go back and watch the YouTube video. I said, you'll probably see that other students came in. I don't know where you were. I think Zoom just sort of messed it up. So if you see somebody or sense that somebody's out there, let me know and I'll go back and check. All right, now where we are now is Chapter 1, Introduction to Differential Equations, and we're in 1.2, which is Initial Value Problems. We've talked about what they are. We're just getting ready to do the first example, which is here on page 16, and that's what you see on your screen. Now they refer back to problem 45 in exercise 1.1 that you were asked to deduce. I don't know if you did this one, that y is equal to c e to the x is a one parameter family of solutions for the simple first order differential equation y prime is equal y prime. Equal y. Okay, that's not that simple. Okay, all the solutions in this family are defined on the interval minus infinity to infinity. No limit at all. If we impose an initial condition, say that when x equals 0, y's got to be 3, then what you do is just simply plug that into this solution. So let's do that. I will go to the whiteboard and we'll do that. Okay. Now I've still got to move this taskbar for the whiteboard out of the way. I'll move it up here and then move the whiteboard as far as I can up and over, so I have the maximum. In fact, I think what I'll move, Jim Manuel, you're in the way again, so I'm going to move our names back over there, so that gives me maximum space. Okay, so what we have here is y is equal to, let me make sure I've got the right end of the pen, I didn't, y is equal to, for some reason this thing will not do equal signs well. I don't know why. I must do them too fast or something. But anyway, y is equal to c e to the x. Now, that's supposedly a one parameter family of solutions to the simple first order differential equation y prime equal y. Well, guess what? That's a good guess anyway, isn't it? What is about the only function you know of that first derivative is the same as the function itself? The exponential function. So this is a pretty good guess. The trouble is you have a constant, an unknown constant in it, c e to the x. Okay? So, and that's good for all values of x, from negative infinity to positive infinity. Okay? Now, here is our initial condition that y, when x equals 0, that's pretty ugly, isn't it? Okay. Y, when x is equal to 0, is equal to 3. All we do is plug that in. Y, well, actually we don't need to write it down again. Let me just erase that. No reason. Okay. Okay. We know that y is equal to 3 when x equals 0. So put a 3 in here for y is equal to c e to the 0. X equals 0, y is equal to 3. Well, what is e to the 0? Anybody? Oh, here comes James. Hold on. Hold that thought. Well, I can't get him to show up. There we go. There's James. I found out when I hold the pen too close to the Wacom. Okay, so we got James here. We're only missing Jesus. We get Jesus, perfect attendance. And guess what, team? The first two classes were both perfect attendance. If we can just get Jesus here, we'll have a full day of perfect attendance. That's wonderful. Okay, the question here was, James, what we're doing, here was a solution, y is equal to c e to the x, of this differential equation, y prime is equal to y, with an initial condition when x equals 0, y is equal to 3. So what we did was plugged in y equal 3 down here when I can get this to show up. Where is it? Okay. Oh, here we go. Y is equal to 3 when x is equal to 0. So you have 3 is equal to c times e to the 0. My question when you came in, what is e to the 0? Anybody? E to the 0? Anything to the 0th power? 1. Very good. Okay. So this would just be c is equal to 3. Whoops, writing on the wrong screen here. C is equal to 3. Well, since you know that, plug that back in here, and your general solution is y is equal to 3 e to the x. Once you know what c is, plug it back in. There's your solution. I mean, that's pretty simple. Okay? Now, what if, on the other hand, we say we know the solution curve has to pass through this point? 1, -2. Well, what is that telling us? What does the 1 stand for? That's the independent variable x. -2 stands for the dependent variable y. So now we do that same equation we did before, but now we do -2, that's your y, is equal to c e to the 1, because x is now 1. Well, I don't know exactly what e to the 1 is. It's an irrational number. But I can still solve this and say that c is equal to -2 over e. Or written another way, -2 e to the -1. And once you know that, plug it back in. Y is equal to 3. No, I'm sorry. -2, whichever way you want to do it, e to the -1 times e to the x. Well, anytime you multiply the same base times different exponent, you could write this as -2 e to the x minus 1. And that's probably the simplest way to write the answer. Okay? Let's see what they got. Y is equal to -2 e to the x minus 1. Got it. Any question on what I did with either one of those various steps that we took? Any questions? If not, let's go and see what they did with the solutions. Still got 4 students here. Yep, got 4 students. Let's go back to the text. And now I got to move y'all out of the way again. Kira, you're in the way again. There we go. All right. So there was the first one, y is equal to 3 e to the x. In the second case, -2 e to the x minus 1. Okay? Now, those two solution curves are now here. The first one passes through 0, 3, when x equals 0, y is equal to 3, that solution curve. These are other, this would just be y is equal to e to the x, this would be y is equal to e to the some other x. Here's y is equal to e to the minus some sort of, negative e to the some number e to the x, and this would be the one that crosses here. Y is equal to -2 e to the x minus 1. The -2 flips it across the x-axis and vertical stretch, and the x minus 1 shifts it one place to the right. So whereas e to the x would have gone through, this is e to the x here, e to the minus x would have been down here, and e to the minus x minus 1 would be over here. So that would be that graph. All right. I think we beat that to death. Okay. Let's move on. Any questions on example 1? Just plug and chug, folks. Now, remember we talked a lot about the interval of definition of a solution. This will be a classic case of where that comes into play. Now they say that back in problem 6, or coming up in problem 6 of exercise 2.2, it's a long way from now, you'll be asked to show that a one-parameter family of solution for the first order differential equation y prime plus 2xy squared is equal to 0. Okay, time out just a moment here. What's the order of that differential equation? There's a differential equation, y prime plus 2xy squared equals 0. What's the order of that? first order. It's an ordinary differential equation because that's a prime. If that had been a subscripted x or y there, that would have been a partial. We're not doing partial derivatives. So that's the ordinary differential equation, first order. The other feature, is it linear or nonlinear? Y prime is to the first power, but y is not. That's to the second power, therefore it is not linear in y. Okay? So, it's a nonlinear. That's okay. All right. We don't know how to solve it yet. We'll get to that later. But what we're going to do now is they just tell us that the one parameter family of solutions for this is y is equal to 1 over x squared plus c, and it says if we impose the initial condition that y at 0 is equal to minus 1, then we will find out what our c is. Okay, so that's what we're going to do next. Let's move to the whiteboard and do that. Okay, if I can get my share to come up. Well, why did it move there? I don't know why. Okay, now again, got to move y'all out of the way. This just messed up everything. Let's move this back up to the top, and let's move this back down. I don't know why I'm having to do all this again. Y'all can't see what I'm doing, but I'm moving these toolbars and taskbars out of my way so I can see the screen. Okay, what was that noise? No new students coming in, so I don't know what made the noise. All right, I'm going to clear what we had there. Anyone need this any longer? Okay, now example 2. Here was our differential equation, y prime, first order differential equation, plus 2x y squared nonlinear differential equation is equal to 0. And why it does that, I don't know. It doesn't do equal signs well. The one parameter family of solutions is this, and it messed that up too. 1 or y is equal to 1 over x squared plus c. There's your parameter c. Now, okay, I don't know what's making the noise. Does anyone? Okay. Here's our initial condition. Y of 0 is equal to negative 1. Okay. Now, so what we'll do is take these values, x equals 0, y is equal to negative 1, plug them in here. So minus 1, that's the y, is equal to 1 over c, because x is equal to 0. All right. Well, that looks pretty obvious that c has to equal negative 1. Agreed? Multiply both sides by c, divide by negative 1. Okay. So our solution is y is equal to 1 over x squared minus 1. Now, if you think about how that's going to look, and I don't draw graphs very well, so I'm going to do my best here to draw somewhat vertical line, somewhat horizontal line. Okay? And we know that x can't be equal to plus 1 or minus 1. This is such a pain in the neck. Plus 1, minus 1, vertical asymptotes there. Ooh, this is ugly. Okay, vertical asymptote there, and vertical asymptote here. Okay. Now, if we did a little bit more work on it, we would see, let's just take x equals 0. When x equals 0, y is equal to minus 1. So that's going to be down here. Okay? Now, where does it go from there? Let's take x equal 1/2. So then you're going to be 1 over 1/2 minus 1 is going to be negative 1/2. 1 over that would be a negative 2. So that would be down here somewhere. Same thing if we chose negative 1, you would be over here too. So here's what this function is doing down there. Okay? I can't draw. Okay? Now, we also look at this and say we have a horizontal asymptote of the x-axis. Y equal 0. That's your horizontal. I don't know what's making the noise. Y is equal 0 is a horizontal asymptote. These are your vertical asymptotes. Okay? Now, where do we go from there? Let's take a value like x equal 2. When x is equal to 2, you have 2 squared, which is 4, minus 1, so that would be 1/3. So when x equal 2, you're down here at 1/3. As you get pain in the neck, okay, somewhere down here. When you get closer to the vertical asymptote, of course, you're going to infinity. So this is what this side of that looks like, and as you go closer to positive infinity for x, you're getting closer to 0 for y. Let's come over here at minus 2, for instance. At minus 2, same deal. You get a 1/3 here, and approaching positive infinity there, approaching 0 here. So here's how that function looks. This is the graph of the function here. This is not the graph of the solution. The solution requires that y at 0 be negative 1. That's that point right here. So the integral of, what do they call it? Definition, interval of definition, is from minus 1. This is only good from minus 1 to plus 1. Notice I put parentheses around there because x can't equal minus 1. Forbidden. X can't equal positive 1. Forbidden. So it has to be anything inside this. So this defines not only what your which curve it is, but also which portion of the curve it is. That's that portion down there between there. So this interval of definition will only be from minus 1 to 1. So there's your solution. It's also the interval of definition. Okay. Now, so I don't know. They go on and talk and talk and talk, but this is the part that makes sense. Well, let's go see what they're talking about. So let me go back to, excuse me, I've got hiccups for all of a sudden. Yes. Say that again. Do we have what? Calculus. Oh, CalcView. No, this is not a Ron Larson book. This is by Dennis G. Zill. He doesn't do any of that stuff that Ron Larson does. As far as I know, you only find that Larson precalculus.com, LarsonLinearAlgebra.com, LarsonCalculus.com. You only find those from Ron Larson. This Dennis Zill, he doesn't even have PowerPoints. Okay, that's how pathetic this text is. Anything by Larson, tremendous support. This one, he doesn't even have a worked out solutions. CalcChat.com, not him. Okay, so that's why I like teaching from Larson. Larson, as far as I know, has not written a differential equation book. So Sorry about that. Good question though. All right, so here's example 2. Let me get Jemanuel out of the way. You're in the way again, Jemanuel. Okay, here we go. Now, when you plug this initial condition in, so x equals 0, y is equal to -1, that gave you this. Okay, we worked it out. Yeah, that -1, that's your y, is equal to 1 over c, which is when x equals 0, that would give you c. C would have to equal -1, so there's your solution. Okay. Considered as a function, the domain is a set of all real numbers for which it's defined, which is only not defined x equal -1 and +1. So this would be a solution or a graph of that equation. But you see, we're not just dealing with the graph of an equation, we're looking at the interval of the solution. So considered as a function, this blue is your graph. Okay, considered as a solution of that differential equation with that boundary condition, then you're limited to this red portion down here. Okay, the largest interval over which that's defined would be from -1 to 1, not inclusive. You would have to have parentheses around them. This part out here doesn't fit your boundary or your initial condition. This part over here, it doesn't fit the initial condition. Only the part down here does. Okay, so that's your, so considered as a solution for an initial value. Okay, now I guess what they're saying, if you didn't have the initial value, then any one of these 3 legs could have been a solution. But once you did have it, that not only defines where it intersects, but that's the portion you're dealing with. Okay, they say see problems 3 through 6 in exercise set 1.2 for a continuation of this example. So you'll be doing 3 and or 5 if you choose to do them. So let's move on to a second order initial value problem. This is example 3. If you go back to section 1.1, excuse me, my throat's getting squeaky on me. I don't know if that will help or not, but it makes it feel better. Okay. Example 9, in section 1.1, we saw that x equals c1 cosine 4t plus c2 sine 4t is a 2-parameter solution for this differential equation, x double prime plus 16x is equal to 0. Okay? Given that this is a solution for that, it says find the solution for the initial value problem. So let's do it. Let's do it on the whiteboard. All right. This time I'm going to move Jemanuel in the way again. Okay, move you over here. Move all of us over there. All right, let's clear the screen. All right, and let's set up. Here was a solution. X equal C1 cosine 4t plus C2 sine 4t. They claim that is a solution to this initial, it messes up semicolons. This second order ordinary differential equation happens also, at least appears to be linear. Okay, x double prime plus 16x is equal to 0. It says find a solution of the initial value problem. So here are your initial conditions. Notice this is plural this time. Why? Second order differential equations require two initial conditions. First order differential equations require one initial condition. Third order differential equations require three initial conditions. So we need to here, here's what they are. X at pi halves is equal to -2, and x prime at pi halves is equal to 1. What's that again? Okay, they gave it to us. That's why I didn't choose it. They gave it to us. But that leads to a pretty good point here. For an initial value problem, okay, now I know sometimes initial sounds like it should be 0, okay, because that seems like where things start, but not necessarily. I don't like the term initial, but that's what everybody uses. I like to say fixed value problem. Give me an x and then give me all the conditions there. And this is an important thing. Once you have a value for this, okay, it's a second order differential equation, so you need the function at that value, but you also need its first derivative at that value. You must use the same value in the parentheses. The t, has to be the same. See, the independent variable here is t, dependent variable is x. So the t, once you choose it for one, it's that for both of them, okay? And if you had it for the function, and this is second order, you also need to have it for the first derivative, okay? So that's two good points that I don't know if that's what you meant to bring out, but what you do, whatever value your independent variable is at, you have to use it for both, all three or all seven, however many initial conditions you have to use the same point, okay? And number two, you need for a nth derivative, nth differential, let's see, nth order, that's not it, nth degree, no, nth order, I had it right, nth order differential equation, you're going to need n initial conditions, all at the same independent value, but you'll need the function, its first derivative, second derivative, third derivative, fourth derivative, up to n minus first derivative. That gives you n conditions, because the function itself is sort of like your zeroth condition, zeroth derivative. It's not a derivative. Then the rest of them, the first derivative is the second one, second derivative is the third one, and so on. So n minus 1 will give you n initial conditions. So what do? We plug it in here. So the first one, x is equal to -2. So let's plug that in. -2 is equal to C1 times the cosine of 4 times pi halves. Wait, what is 4 times pi halves? That would be 4 halves pi. Well, 4 halves is 2. That would be 2 pi plus C2 sine of 2 pi. Because again, 4 times pi halves is 2 pi. Now, what is cosine of 2 pi? Anyone know? I'm going to have to talk with some of your trig teachers. Of 2 pi. Nope. Sine of 2 pi is 0. This is 1. Yeah. So this will be just C1, and then like I just said, sine of 2 pi is 0. So this gives you nothing, except you just got what C1 is. C1 is negative 2. Okay, next one we have to take a derivative first. So let's take a derivative of your function, and that would be x prime is equal to, now derivative of cosine is what? Derivative of cosine is what? Negative sine. So that would be negative C1 sine of 4t, but then you do the chain rule, and derivative of 4t would be 4. So that's why I put that in front. Derivative of sine, however, is cosine, exactly, of 4t, and then your chain rule has you derivative of 4t is 4, so I'll put that in front. So there's your y prime at every value of t. Well, we want it only at pi halves, so let's do the same thing we did before, and there the first derivative is 1, so that's going to be 1 is equal to, and we already know what C1 is, it's negative 2. So it's negative 8, because C1 is negative 2. Oh, I'm sorry. Positive 8 times the sine of, but for t, where t is pi halves, that is 2 pi. Plus, I left off my C2 here. Sorry about that. 4 C2 times the cosine of pi halves. Anyone remember what the cosine of pi halves is? Wait a minute. No, that's not pi halves. It's 2 pi. Wait a minute here, folks. That's 2 pi. It's 4 times 2 pi halves, which is 2 pi. Okay. Sine of 2 pi, again, is 0. Cosine of 2 pi, as Ryan said earlier, was 1. So this gives you that 1 is equal to 4 times C2 times 1. So therefore C2 is equal to 1/4. Divide both sides of the equation by 4. Whew, goodness gracious, this is a rough thing. I found out part of what my issue was there, not being able to write well, is that my shirt tail got caught under my pen, so it wasn't writing. I don't know about where you're living, but we're getting our daily rainfall here where I live. It seems like we've gotten rain every day for I don't know how many days. I'm not complaining. I like the rain. All right, so what is our final solution? Our final solution, go back to the original solution here. X is equal to C1, we found out to be negative 2 times the cosine of 4t plus 1/4 times the sine of 4t. Oops, 4t. Okay, 4t. That's it. Notice when you have an initial value problem and have all the initial conditions you need, you wind up with a parameter-free answer, a specific solution. And in your text, you see x is equal to minus 2 cosine 4t plus 1/4 sine 4t. That is your solution. All right, so let's go back to the book. Any questions on that before we leave it? Okay. All right, now I've got to move Ryan out of the way. He's in the way again. Okay. Now, just to keep from dropping this expensive pen, I'm going to put it on the shelf here. When you plug these values in here, first apply x at pi halves to be -2. That's what your initial, the first initial condition tells you. It's sort of like a double initial there. To the family resolution, you get C1 cosine 2 pi plus C2 sine 2 pi, but sine 2 pi is 0. So therefore, and you know that's got to equal -2, and since cosine 2 pi is 1, then C1 has to be -2. C1 is equal to -2. Next, apply x prime, defined at pi halves. Sorry. Let me see if water will help. I've been talking too long today. Okay. So we get C1 is equal to -2. In order to apply the second initial condition here, you first got to take the derivative. So you differentiate the original problem. Now you can go on and put in the -2 for C1. I didn't, but you could have. And differentiating and then setting t equal to pi halves, which is what it says here, and x prime equal 1, which it says here, it gives 8 times the sine of 2 pi plus 4 C2 times the cosine of 2 pi is equal to 1. And because sine of 2 pi is 0, that gives you 4 C2, and cosine of 2 pi is 1. So you get 4 C1 is equal to 1, meaning that C2 is equal to 1/4. So plugging that back in here, we have C1, which is 2, or -2 cosine 4t plus 1/4 sine 4t, and that's exactly what we got. Now, let's move down to another question here. Actually, two questions. Two fundamental questions arise in considering an initial value problem. The first of these, do we even have a solution? Does a solution for this problem even exist? Now, if it does exist, is it a unique solution or one of many solutions? Now, remember, when we have a 1 or 2 parameter system, you have graphs all over the place, a whole family of solutions, infinite number of solutions. But then when you have your initial values and you get down to, like we just got, one with no parameters in it, does it exist? Well, for the first order initial value problems, okay, the question, does the differential equation dy dx equals some function of f of x and y possess solutions? Now, the second question, do any of those solution curves pass through the point x0, y0, if that is your initial condition? Now, goodness gracious, my eyes are dry. I don't know what's going on here. My nose is stopping up. I've got my ceiling fan on. Maybe the fact it's raining outside. I don't know what's going on. Okay. The uniqueness question, when can we be certain that there is precisely one solution curve that passes through the point, not a whole family of them? Okay. Now, examples 1 and 3, when we were doing those, I sort of pointed out, I think on 1, but I forgot to on 3. It says a solution is used rather than the solution. The indefinite article A is used deliberately to suggest that there's possibility of other solutions may exist. At this point, it has not been demonstrated that there is a single solution for each problem. Here illustrates a initial value problem with two solutions. I think it's one we've already seen before. So let's take a look at it. Example 4. Okay. All right. Here is your differential equation. dy dx equals x y to the 1/2. Now they suggest two solutions. Y is equal to 0. If y is equal to 0, dy dx is equal to 0. And if y is equal to 0, the square root of y is equal to 0. You have 0 equals 0. Well, that's a trivial solution. Okay? So that's a solution. But they also claim that this one, y is equal to 1/16 x to the 4th, and we've done this one before, that indeed is a solution as well. So here's the trivial solution, the red line, and here's the other solution, the blue line. Okay? Now, I guess there's times when it's important to note that there is a trivial solution to a problem, but it just seems like it's not a very interesting solution. It seems like the next one will give you far more information. Okay? But it is a solution. So it does have two solutions. Now at 0, 0, they both meet, so that is fine. So if you had your initial condition at y of 0 equals 0, both of them fit. Both of them fit. At that place, both of them fit. Now at some other point out here, your trivial solution will not work. But at that point, they both work. So within the safe confines of a formal course in differential equations, one can be fairly confident that most differential equations will have solutions, and that solutions of initial value problems will probably, notice how they put these Wiggles words in here, probably be unique. Real life, however, is not so idyllic. Therefore, it's desirable to know that the is desirable to know that in advance of solving a differential initial value problem of whether a solution exists, and when it does, whether it is a unique solution, the only solution to the problem. And it says, since we're going to consider first order differential equations in the next 2 chapters, we state here, we're only going to do chapter 2, we're not doing 3. We state here, without proof, a straightforward theorem that gives conditions that are sufficient to guarantee the existence and uniqueness of a solution of a first order, initial value problem given in that original form. It says we'll wait until chapter 4 to address the question of the existence and uniqueness for second order and higher differential equations. So here is our theorem without proof. We're just going to take their word for it. Excuse me just a moment. Goodness gracious, I don't know what's going on today. Here's the theorem. Let R be some rectangular region in the xy plane defined by x is between A and B and y is between C and D. So you have your xy plane here, rectangular region, between A and B on x, C and D on y. That contains this point x0, y0, somewhere in the interior, not on the boundary, in the interior there. Okay? If, well, that happened, I don't know. If f of xy and the partial of f with respect to y are both continuous. Now here we've hit the first time that we're dealing with partial derivatives. And I think every one of you except I can't recall. Have all of you, I know several of you are in Cal 3 now. I know Kara is, James I think is, Jemanuel is, and Jesus is. I can't remember about Ryan. Have you already finished Cal 3? Ryan? Have you already finished Cal 3 or are you? Yeah, I thought so. But the rest of you are in Cal 3, right? I believe that's right. Okay, so you haven't gotten to partial differentials yet. Now remember, we're not doing partial differential equations, but we're going to have to take a partial derivative. So just for now, this is a partial derivative of f with respect to y. Remember, f is a function of two independent variables now. So if f is continuous of those two independent variables on that region x, rectangular region on the xy plane, and the partial of f with respect to y is continuous in that region R, then there exists some interval I0 near that point x0, y0. Okay, so x0 minus h to x0 plus h, y0 is also a little bit, as long as h is greater than 0, contained on AB, and the unique and there is, let's see, contained in it, and a unique function y of x defined on that interval I0, that is a solution of the initial value problem. Now that's a lot of blah 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 there, but here's the key. The function has to be continuous, and its first partial with respect to y has to be continuous. Now, don't know if this is going to be helpful or not. It may actually be confusing. Let's go back to this one. Okay. Let's not. I think that'll get too confusing. I think the next example will be better. Okay. The foregoing result is one of the most popular existence and uniqueness theorems for first order differential equations because of the criteria of continuity of the function, okay, and of the partial of f with respect to y are relatively easy to check. The geometry of that is illustrated in that theorem, illustrated in figure 1.2.16, which is this right here. Okay. Here is a rectangular region. Here's your A on x, your B on x. The function has to be in between those two. Here's a C on y, there's a D on y. The function has to be somewhere in that region. Okay? So that's what we're doing. Here's the point x0, y0. Anywhere in here would work. Okay? Now, here's the function going through there. Okay? The I0, that interval that's within the rectangular region here, has to be within that, within some fairly short distance of x0. x0 plus or minus h, some small value h. Okay, now just has to be small enough so it stays in the region. Notice we did not put a limit on the y. I guess you could, but it's not necessary at this point. Okay, now basically if you have that, here's what they're saying. If you meet those criteria and the function is continuous there, and the partial of the function with respect to the independent variable, which we haven't really talked about that, but that would be the partial of alpha with respect to y is continuous too. Now there's nothing in this picture that illustrates that true. Obviously the function is continuous there, but the partial with respect to y, that's not quite so obvious unless you think of this. There aren't any corners or cusps or other things like that. So it's a nice smooth function. So basically this is continuous, and this is the fact that's continuous means the function itself is smooth. So let's get back to example 5.4. Example 5, which is revisiting 4, okay, which one we just did. All right. We saw in example 4 that this differential equation, dy dx equal x y to the 1/2, possesses at least two solutions whose graph pass through 0, 0. Now, here's what we're going to do, and this will probably be a pretty good place to do it. Okay, now in the first place, f of xy, xy to the 1/2. Okay, now at 0, 0, when y is equal to 0, let me tell you something. Okay, forget about x for now. Y goes up very steeply there because you're making half of a parabola, half of a sleeping parabola, I call it. The derivative at that place where x equals 0 is infinite, not finite. That's the reason, excuse me, that it doesn't have a unique solution there. The partial of alpha with respect to y there does not exist at 0, 0, and therefore you don't have a unique solution. Now I said let's take a partial, so let's go back to the to the whiteboard, and let me take that partial derivative. So for those of you who haven't had it, you'll see that. Let me go on. I've got to move people around again. James, in the way again. All right, let's clear the drawings here. Okay. I tell you, I don't know why. I think what I did, I must have eaten lunch too fast because I only had 30 minutes between my first two classes and 30 minutes between the second one and this one. I must have just crammed it down too fast because, man, I'm so dry. Okay. Let me get my pen and the board. Okay. So here is the function. Here it is. Okay. Here's the difference. Yuck. I don't know why that did that, but let me clear it again. Okay. Now, here is dy dx, okay, okay, here we go. Dy dx is equal to, just won't draw an equal sign right, x y to the 1/2. Now what they're calling this thing is f of xy. Okay, that's what the derivative is, some function of x and y. Remember, this is what we called the, was it standard form? They had some name for it. Okay, that's your f of xy. Now, number one, is that continuous at 0, 0? Certainly 0, 0 fits there. Is it continuous? Only from the right-hand side. So that's one issue. But the second issue, they said take the partial of this f. So the partial of f, and they did it in this notation. I had an old guy, I'd never heard this before in my life, with respect to y. An old guy who took all 3 calculus classes last year or the year before, sometime recently. He called that symbol for a partial derivative curly d. And it makes perfect sense. I mean, I never knew what to call it. I just called it the partial of f with respect to y. He called it, whereas this up here is a d, he called that a curly d. And that's indeed what it is. Now, this is taking of y. This is taking of your function of x and y. So you do have two independent variables here. Here, your only independent variable is x, dependent variable is y. So don't get these crossed up. This f is not that y. Nowhere. This f is that xy to the 1/2. So number one, we've already noted that this f of xy is not continuous at 0, 0 because it terminates at y is equal to 0. It initiates there and goes up from there. It doesn't continue. But let's take the partial. When you're taking the partial with respect to a variable, we take it with respect to that, let the other variable, if it shows up there, remain constant. So the x is going to treat like a constant. So this would be 1/2, because you're taking the partial with respect to y. 1/2 times x, so I'm going to make that x over 2, times y to the minus 1/2, because you're taking the derivative of a power function, happens to be a fractional power. We subtract 1 from 1/2, you get negative 1/2. Well, this is the same as writing x over 2 times the square root of x. Okay? Square root of y, I'm sorry. That is the derivative of that. Is that continuous at x0, y0? It's not even defined when y is equal to 0, because you cannot take the derivative here. So there's 2 reasons that this does not guarantee to have a unique solution. Number one, the function itself, f of xy, is not continuous at 0, 0. It reaches 0, 0, but it doesn't extend past it. But even more telling is the partial of f with respect to y is not even defined at y equals 0. You can't take it at y equals 0. You get an infinite answer. So for 2 reasons, but this is the strongest, that why that does not have a unique solution. All right. I think we beat that into the ground. And by the way, that was the bottom of page 17 and the top of page 18. Okay. Now, let's go back to the text. Okay, now I got to move you again. Manual in the way again. Okay, there you go. All right. Now, let me set this down so I don't drop it. Okay. Now, if we had were under investigation of the point x equal 2, not x equals 0. We're looking at things that pass through 0, 0. But if it had been x equal 2, no sweat there at all, because, and we can come back up here and see, at x equal 2, up here, there is only one solution. And why is there only one solution? Because the function is continuous there, the xy to the 1/2 is continuous there, and its derivative is continuous there, okay? Because its partial with respect to y is continuous there, because no problem taking the square root of 1. That's just 1, okay? It's taking square roots of 0 in the denominator. You can't do. Okay. Now, if you go back to example 1, way back, the theorem guarantees you no other solutions for that initial value problem. If you remember what that one was, the differential equation was this: y prime is equal to y. Your initial value was y of 1 was equal to -2. I'm sorry. X equals 0, y is equal to 3, and then we did a second one that when x equals 0, y is equal to -2. Each of those produce one and only one solution, and the reason this value here is defined everywhere. There aren't any issues with any of that. Okay? Now, if you took the f of xy is equal to y. Okay, yeah, that was your initial problem. Y prime is equal to y. So this was your f of xy. And f of xy here is the partial of that with respect to y. It's just derivative of y, which is 1. Okay? Here is your y itself, defined everywhere. This is defined everywhere. So sure enough, this will be a unique solution. Now, how about those, like we just saw, that have some unique solutions, but other places they don't? So obviously, there has to be some interval over which that existence and uniqueness would happen. Existence we saw in the earlier, when you had the curves that went like this and like this, then you had to be somewhere on your interval could not include one of those vertical asymptotes, obviously. Okay? Now, the other issue that we have is that first partial derivative of that, and as long as that's met, then you have unique solutions. So there may be places where there's interval of existence, okay, we saw in that one problem, or intervals of uniqueness. For instance, the one we just did, the x's have to be greater than 1 because it's not continuous or it has that first partial defined at x equals 0. Y is equal to 0. Doesn't happen there. Okay, so suppose that y of x, which is your function on the right hand side of your differential equation, represents a solution. I'm sorry, this is your solution for your initial value problem. the following three sets of real on the real axis may not be the same. The domain of a function y of x doesn't have to be the same as the interval. We saw that, okay? When we had domains that were here and here, the interval had to be in one of those three. So the domain would not be the same, okay? Okay? The interval I over which the solution is defined or exists, okay, the first is the domain of the function, the second one is the interval I over which it exists, and the third one is the interval I of existence and uniqueness, okay? So in other words, you could have an interval of existence, but it may not include in it that uniqueness at that same place. So example 6 in section 1.1 illustrated sorry, the difference between the domain of a function and the interval. So I think we've beat that into the ground. I'd say let's move on. Now these remarks at the end of the section sometimes are helpful. The conditions in theorem 1.2.1 are sufficient for uniqueness and existence and uniqueness, but they're not necessary. Sufficient but not necessary. That means that when f of xy and the partial of f with respect to y, yes. Oh, it's time, isn't it? Okay, well, we're right at the end. Thanks for catching it. Right at the end. There's nothing really spectacular in these remarks. Most of the time I don't even do them. I thought I had time to. I don't see anything here. Now, here's one place. Boundary conditions. We're going to talk about that in a coming up section. So don't sweat these now. These are different from initial conditions because, if Ryan pointed out, initial conditions have to be at the same point. Boundary conditions do not. Here's a boundary condition at x equal 1, y is equal to 0. At a different x equal 5, y is still equal to 0. That means that these two places, two different x's, you have boundary conditions, not initial conditions. Or you could have y at pi halves right here, but y prime over here at pi. Those are boundary conditions, not initial. So we'll deal with those later. I don't think there's any homework exercises in there. They said see problems 39 to 44. So here's the homework exercises for today. Do number 1, either 3 or 5, and by the way, answers to the odd number problems are in the back of the book. There is no calc chat, Ryan. There is no calc view, Ryan. Only back of the book, old school book. 1, 3 or 5, 7 or 9, and then 11 or 13. Okay? Now, 15, any of the odds 17 to 23, 25 or 27, and then it's hard to show on one thing here. You can do 29 and or 31. Now I have to scoot back up to the top of my next column, and or 33. Okay, any one of those three, 29 through 33. Okay, then either 37 or 39, 35 or 37. There's 35 and there's 37. Okay, and any of the odds 39 to 43. All these should be in the back of the book. If you run into any other not in the back of the book, don't worry with them. Anything past when they start talking about discussion problems, most of the time they're not in the back of the book. If you do find some that are, you can look at those as well. But basically stop here at 43 because most of those will be in the back of the book. All right, good deal. Any questions on what we covered so far? Sorry, we did run out of time. We'll pick up next time in 1.3. And this is going to be mostly show and tell. We're not going to be doing that many exercises with it, just sort of show and tell. Differential equations with mathematical models. Once we finish 1.3, I'll be giving you the first test. Okay? So it's coming up probably on Thursday. In fact, I'll probably give it to you on Thursday whether we finish 1.3 or not, just so you'll have the long weekend that you can work on it. Because they won't be due the next Thursday if we haven't finished 1.3. They'll be due a week after that. So it'll give you more time to work on it. All right, good deal. Any questions? All right, we will pick up and go from there next time. Sorry we went over. Whoa, several minutes, 7 minutes, but guess what? No extra charge today. I'm tired of sharing, so I'm going to stop the sharing now. Any last thoughts, parting shots, questions before we leave today? All right. If not, we'll see you on Wednesday. So I'll be ending the meeting for everybody. I'll try to remember to download.